In 2007, a radio telescope in Australia picked up a burst of energy lasting 5 milliseconds that had traveled billions of light-years to reach us. It carried more energy than the Sun produces in a day. Scientists still do not fully know what sent it. In 2007, astrophysicist Duncan Lorimer and undergraduate student David Narkevic were searching through archival data from the 64-meter Parkes Observatory in New South Wales, Australia. Among the recordings from July 24, 2001, they uncovered an isolated spike of radio waves, an event that had remained buried in the station's digital files for 6 years. The signal lasted just 5 milliseconds. In that tiny sliver of time, the unknown source released a burst of radio energy equivalent to 80 days of our Sun's total output. But it was the structure of the arrival that shocked the researchers. As radio waves travel across space, they pass through ionized intergalactic plasma. This thin gas acts like a cosmic prism, slowing down lower frequencies so they arrive at Earth slightly later than higher frequencies. The Parkes signal showed a massive frequency delay, known as dispersion. This delay meant the waves had pushed through billions of light-years of intergalactic space, well outside the boundaries of our Milky Way. To travel that distance and still register as a bright flash at the telescope required an engine of unimaginable power. For astronomers, a brief extragalactic flash of this scale seemed physically impossible. It was a single, unexplained pulse that challenged known physics. The scientific community met the 2007 announcement of the Lorimer burst with deep skepticism. Many astronomers suspected that the miraculous signal was nothing more than a local glitch. Their doubts hardened when the Parkes Observatory began detecting more of these ultra-short, sweeping radio flashes. These newly discovered signals, named Perytons after a mythological winged stag, possessed almost the exact same mathematical properties as the original space burst. Yet, they appeared in all 13 beams of the telescope's receiver simultaneously, a clear sign of a terrestrial source rather than a distant cosmic engine. For years, these false alarms paralyzed fast radio burst research. The mystery remained unsolved until 2015, when astrophysicist Emily Petrov and telescope technician Paul Hobbs decided to run a series of forensic tests at the facility. Hobbs had noticed a strange pattern. The Perytons seemed to cluster around standard meal times. The team began systematically operating the observatory's kitchen appliances while tracking the telescope's data. They discovered that if a researcher opened the microwave oven door before the timer finished, the active magnetron released a brief, sweeping burst of radio waves. The telescope swallowed this leakage, registering it as a signal from the stars. This domestic culprit had stalled a new era of astronomy, leaving scientists to wonder if any of their cosmic detections were real. In September 2018, a massive new instrument came online in the mountain valleys of British Columbia, Canada. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, looked nothing like a traditional telescope. It consisted of 4 giant metal cylinders, each 100 meters long, resting silently in the wilderness. CHIME had no moving parts. Instead of tracking a single star, its stationary design mapped the entire northern sky every day as the Earth rotated. A specialized GPU-based digital pipeline processed the incoming data in real time, scanning millions of signals every second to separate local interference from actual space phenomena. CHIME's massive field of view changed the entire discipline. Within its first year of operation, the telescope detected over 400 fast radio bursts. By the end of 2020, that number surpassed 1,500. Before this operational start, astronomers debated whether these flashes were real cosmic events or merely instrumental glitches. CHIME resolved the doubt with sheer numbers. This sudden flood of data shifted the investigation from cataloging rare anomalies to analyzing a massive, active population. Researchers began looking for hidden patterns within the noise. Why did some sources burst only once, while others seemed to flash repeatedly? The search was no longer about finding a needle in a haystack. It was about deciphering the structure of the haystack itself. In November 2015, the massive 305-meter dish of the Arecibo Observatory in Puerto Rico recorded something that upended the foundational assumptions of the entire field. A single sky coordinate known as FRB121102 flared multiple times within a 3-hour window. By 2016, researchers confirmed this was no fluke. The source was repeating. This repetition destroyed the prevailing theory. If a source could fire again and again, the signal could not be the dying scream of a cataclysmic collision. A star could not destroy itself twice. Astronomers used the European VI-LBII network to pinpoint the exact home of FRB121102, tracing the signal to a dim star-forming dwarf galaxy roughly 3 billion light-years away. Then, the mystery took a stranger turn. CHIME detected another repeating source, FRB180916. This signal did not fire at random. It operated on a strict 16-day cycle. 4 days of constant erratic activity, followed by 12 days of absolute eerie silence. This predictability forced scientists to consider new, complex dynamics. Perhaps the source orbited a companion star that periodically eclipsed the signal, or a highly magnetized stellar remnant was precessing in the dark, slowly sweeping its beam past Earth like a cosmic lighthouse. The steady heartbeat of FRB180916 suggested a system governed by precise mechanical clockwork, leaving researchers to grapple with a troubling reality. The universe was producing multiple distinct classes of cosmic engines. On April 28, 2020, the search for answers took an unexpected turn inside our own galaxy. 2 separate instruments, the CHIME telescope in Canada and STARE-2 in the United States, independently captured an incredibly bright millisecond-long radio blast. This time, the signal did not travel for billions of years across the intergalactic void. It originated just 30,000 light-years away, within the constellation Vulpecula. Astronomers traced the burst directly to SGR 1935 plus 2154, a magnetar, a highly dense neutron star possessing a magnetic field trillions of times stronger than Earth's. This single galactic event provided the first direct evidence linking a fast radio burst to a known, observable astrophysical object, offering a tangible laboratory to test how these extreme cosmic engines actually operate. To explain how a magnetar produces such violent outbursts, theorists point to starquakes, catastrophic ruptures in the neutron star's ultra-dense crust that release immense magnetic energy. Yet, some researchers explore more radical ideas. Astrophysicist Avi Loeb proposed that a fraction of these bursts could theoretically stem from artificial transmitters functioning as interstellar beacons or light-sail propulsion systems. To test this hypothesis, the Breakthrough Listen initiative targeted known repeating sources with high-resolution spectrometers. Every scan returned a null result. No fast radio burst has ever exhibited the narrowband carrier waves or structural modulations that would suggest an engineered origin. A galactic magnetar provides a promising source candidate, yet this single model fails to explain the entire cosmic census. Some radio flashes never repeat. Others originate in ancient dead galaxies where young, highly active magnetars cannot exist. Predictable periodic cycles still defy simple stellar explanations. Today, instruments have catalogued over 7,000 bursts, but fewer than 70 have been traced to a precise home. Among the vast, unmapped majority sits the original 2007 Lorimer burst, leaving astronomers with a quiet, lingering uncertainty. They may be looking at entirely different classes of cosmic engines. Today, instruments like CHIME continuously monitor the void, capturing thousands of these fleeting transmissions. Yet the silence between the bursts remains deafening. We are left staring into an unpredictable cosmos, wondering what or who is calling out. Share your thoughts in the comments below.